Yes, my dear friends, we move on to the next one, and that is about redistribution reactions. I've already explained to you in my previous videos about the various properties involving organometallic compounds. Under that, the first one was reaction with oxygen and halogens. Then we discussed about alkylation and arylation. Then we discussed about reaction with protic reagents. So here we are on the fourth property. You can just check it out. It's written on the board, and that is about redistribution reaction. So what is exactly redistribution reaction? That I'll explain you, and then I'll give you some examples. So in this redistribution reaction, we are talking about derivatives of same element combining. So there is going to be exchange of groups taking place, and such reactions are called as redistribution reaction. Now, which derivatives we talk about? We talk about alkyl or aryl, and the other one is going to be the halide. Okay, so we have an alkyl derivative and we have a halide derivative of the same element. Group exchange takes place, and that particular reaction is called as what? Redistribution reaction. Not understood? No problems at all. I'll give you some examples so you understand this very well. So let us take the first example, and that is HgR2. I'll write down in this manner so that you understand this very well, with HgX2. Same element, mercury. This is an alkyl or aryl derivative. This is a halide derivative. Now see what happens is, one of the bond of the Hg and the R is going to break. One of the bond of the Hg and the X is going to break. Okay? The X will come to this mercury. The R will go to this mercury. So what do you get now? I hope you understood now. The product form will be, yes, it's going to be Hg. Okay. Next is, one X is as it is, one R is as it is. Only thing now is what is happening is this R goes over here, this X comes over here, and as a result of which we get HgRX. Two molecules. Okay, two molecules of what? HgRX. Same way, I'm also going to talk about Zn, zinc, with the alkyl or the aryl derivative, and zinc with the halogen, that is a halide derivative. So alkyl or aryl derivative and the halide derivative, same reaction. So we will be getting two molecules of ZnRX. Right? So these are some simple examples. Some more examples we'll be considering, and that is, let us take an example of Br3, boron, valency is 3, combining with Bx3. Now here what happens is, I am showing a transfer of 2R from Br3 to Bx3 and 2X from Bx3 to Br3. Okay? So see what happens is, when the 2R group goes off, only one remains, and the 2X is going to come from this side. So I get Brx2. You understand this? The 2R going over here and the 2X coming on this side. So we are having Brx2 plus. Now here see what happens is, the 2R, I write down boron first of all. The 2R from Br3 is going to do this boron. So I write down as Br2. And the 2X is going on the other side. So how many X remains? 1X. So we get Br2X. Okay, so you cannot write down like the ones which I've written over here, the two molecules. No, you cannot. Okay, this is the way you can write down. Similarly, Gr4, I'm going to treat with Gx4 here I am going to show only one R going on the other side and the one X going on the other side. So what I am going to get is GER3, one R goes on the other side and one X comes over here. So GR3X plus here only one of the X goes. So that means I will be having GX3 and only the one R comes on the other side. So this is what we have. So GR3X plus GX3R. You getting it? Right. Now, we also have some reactions with respect to tin. Under different conditions, it is going to give you different products. So let us check it out. SnR4 plus SnX4. Now, please be very careful, my dear friends. And that is that when you talk about germanium and tin, okay, they are elements belonging to the same group. A carbon family it is. Carbon, silicon, germanium, tin, lead. Alright, so the first step is the same. The temperature is going to be around say 273 to 293 Kelvin. So I'm just replacing the germanium by tin. So I'm getting SnR3X plus SnX3R. Alright, now if I increase the temperature, that means I'm going to take this product, so the first step as a reactant of the second step. So SnR3X plus SnX3R, okay, at a temperature of around say 450 Kelvin. Then what happens is one more R goes on the other side and one X comes on the other side. So what am I going to get is SnR2, one R goes on to the right hand side, so it will be SnR2. 1x comes from this side, so there is already 1x, so I'll be getting x2. And the same thing is going to happen over here also, my dear friends. This R goes on the other side, so I will be getting R2. 1x goes on the left hand side, so therefore I get this. So I'll just simply write it down as what? Two molecules of the dihalide, dialkyl aryl derivative of tin. Alright, so this is, my dear friends, some of the examples of redistribution reaction. Make it much more simple, and that is I am going to consider two derivatives of the same element and the groups are going to exchange. The two products that I get, that is a part of the redistribution reaction. Okay, so the two derivatives are, first one is the R group, which can be either the alkyl or the aryl, and the second one is going to be halide. So basically we are talking about an exchange taking place between a halide ion and the alkyl ion or the aryl ion. Okay, so this is, my dear friends, the fourth property of the organometallic compounds under the heading of redistribution reaction. And I hope you have well understood this very well. So, my dear friends, we discussed the last property now, and that is about complex formation reactions under organometallic compounds. So, under this category, what we need to learn is that there are certain organometallic compounds which are electron deficient. Okay, that is having less number of electrons. So as a result of which, they have a tendency to expand their coordination number. Now, what are the methods by which they are going to do it? The methods are like, we have self-association, combining along with itself, okay, to form dimers and the trimers and the tetramers and so on. Or it can be through addition reaction, resulting in the formation of adducts. And the third and the most commonly used method is combining with a complexing agent, which we very well known as ligands. So these are the ways and methods by which they can expand their coordination number. Now, because they are electron deficient, and therefore they will have a tendency to accept electrons, and hence these organometallic compounds which are electron deficient will behave as Lewis acid. And when I am going to talk about combining with the complexing agents, that is ligands, which will behave as Lewis base, some of the examples which can be considered is amines. Okay, we can also talk about say ethers and so on. Okay, I'll give you some examples so that you understand this very well. Let us first of all take an example of a dialkyl derivative of beryllium. Okay, alkaline earth metal. So we have BeR2 being treated with Me thrice. Trimethanamine. So this is a tertiary amine. There is a lone pair of electron on nitrogen. So this is electron deficient. And this is electron rich. Alright? So this pair of electrons will go towards what? The beryllium, resulting in the formation of a coordinate covalent bond. And the reaction can be represented as R2. I write it on the other side so that you understand how exactly the bond formation is taking place. So this is the way it is going to be, Me thrice. Right? So this is what is the bonding, and that's called as a coordination compound, and thereby we say beryllium increases its coordination number. Alright? Now the other examples which can be considered, okay, under this particular category is that we talk about the Lewis acid character. This was of group 2. Now I consider group 3. No. In the sense, which group 3 I am talking about? Not the conventional group 3. I am talking about group 3 with respect to the main block elements, the main group elements. So with respect to the main group elements, the group 3 means what? Yes, it's actually group 13. That is the boron family. So let us have a discussion about that. Okay, boron family is also going to be electron deficient. So how are we going to think about the order of strength of the Lewis acid character amongst the trialkyls of the boron family? So let us just check it out. So the order of strength of the trialkyls of group 13 in terms of its Lewis acid character. So how it is going to be? We talk about first of all group 13 elements. The first one is boron. I am going to consider this as say Br3. After boron is aluminium, so we have AlR3. After aluminium is gallium, so we have GaR3. After that we have indium, so that is InR3, and then thallium R3. Now see, it all depends upon the Lewis acid character, my dear friends. It's all about gaining of electrons. So one of the most primary requirement of gaining an electron is presence of unoccupied orbitals. Greater the number of those unoccupied or the vacant orbitals, greater is the tendency to accept electrons, and therefore greater is the strength of the Lewis acid character. Okay, it's as simple as that. So we need to check it out. Where are greater number of unoccupied orbitals? So as the size increases, the number of orbitals also increases. When you talk about simple example is boron, and I'm talking about thallium. So boron doesn't have a d orbital. It only has an s and the p orbital. Okay, so boron with atomic number 5 has a configuration of 2s2 and 2p1. So we say that only p orbitals are vacant. But here in this case, when you talk about thallium, there are going to be the d orbitals also which are going to be vacant. Okay, because there is the presence of d orbitals as well. Okay, there are going to be f orbitals also which is coming around. Okay, so the greater is the number of unoccupied orbitals, greater will be its ability to accept electrons. Okay, when we talk about TlR3, alright, and hence the Lewis acid character will be highest. Okay, so TlR3 will be having the highest strength of the Lewis acid character, and Br3 will be least. Alright, so I hope you have understood up to this. We still need to continue with respect to complex formation with some more examples, but then before I consider some more examples, please have a look at it and see whether you understand this very well. Yes, my dear friends, some more examples we will be considering now, and that is with respect to aluminium. Now actually aluminium forms a dimer, and the formula of the dimer is Al2CH3 Okay, it's a dimer of trimethylaluminium. Now when this combines with a tertiary amine, say NC2H5 thrice, there is a lone pair of an electron on nitrogen. So that is going to be given to aluminium. Now the product which is going to be formed, please have a look at it. The product will be CH3 thrice. Here it was 6, now it is thrice. Al and C2H5 thrice. And the bond is going to be formed between nitrogen and aluminium. Now what this reaction actually suggests, my dear friends, and that is, I'll first of all explain you the structure of this, how exactly it is, so that you are in a better position to understand how the reaction actually takes place. And how are we going to account for the bond strength. Now see, this is what is the structure of Al2CH36. There are 6 methyl groups. The 4 methyl groups are the terminal ones. And these 2 are going to be the bridging ones. Bridge means connection. So they are connecting the 2 aluminium. So these 2 are bridging and these are the terminal ones. Now the formation of this product suggests that there is going to be a bond breaking taking place. That means which bond is going to break? The bond between the Al and the CH3, that is the bridging one. And this bond also is going to break. So we have, see this, Al, CH3, CH3. So this is going to combine with the molecule of the trimethyl ethyl amine. Okay, and similarly here also see this bond is going to break. So this is a clear indication that the Al-CH3-Al bridge bond is weaker as compared to the terminal Al-CH3 bond, because the terminal Al-CH3 bond remains as it is during complex formation. It's only the bridging bond undergoes breaking. Alright, so this is what is being suggested, that is the bridge Al-CH3-Al bond is weaker as compared to that of the terminal ones. Alright, so I hope you understood this. Now we talk about, my dear friends, about group 14. Now in group 14 what happens is the tetra positive oxidation state plus 4. I'm talking about carbon family. So in the tetra positive oxidation state, the configuration is NH2 and NP6. Now you will say how it is NH2 and NP6. It is in the tetra positive oxidation state I am talking about, my dear friends. Okay, otherwise you will say carbon is, and the silicon and the germanium will be NH2 and NP2. How is writing NH2 and NP6? But please be very careful, it is in the plus 4 oxidation state. Now, because it is NH2 and NP6, it is going to be a stable octet. So generally, they do not have a tendency to expand their coordination number. Yes, but when it is going to combine with highly electronegative species, then it does expand its coordination number from 4 to it goes to say 5 or 6 or 7 as well. I give you a simple example, and that is about SiCl twice, AC twice, acetyl acetonate. Okay, now this is a bidentate ligand, so total number of donor atoms are going to be 4. Here 2 chlorine, so 4 plus 2 is 6. So therefore the geometry becomes octahedral and the coordination number goes to what? 6. But this is, as I said, my dear friends, only when the group 14 elements are going to combine with highly electronegative groups. Otherwise, generally, with the plus 4 oxidation state, it has got this inert gas configuration, so it doesn't have a tendency to expand its coordination number. Alright, so this was, my dear friends, about group 14. Now, my dear friends, we'll just talk about the character of a Lewis base. Lewis base means electron rich. Okay, so I'll just give you some example with respect to group 15. We have N-Me thrice. Next we have is P-Me thrice. Next we have is AS-Me thrice. We have SB-Me thrice. Each of which has one lone pair of an electron. Now the one which is going to donate the lone pair of electron very fast is going to be a strong Lewis base. So here in this case, who is going to donate fast? Obviously it's nitrogen, because nitrogen has a smaller size. So the electrons are very close by. And there is a lone pair of electron over here. So electron, there is going to be repulsion. And hence, it is going to have a greater tendency to give away the electrons very fast. And therefore, this becomes the order. What is this? This becomes the order of the strength of the Lewis base. Okay, when we are going for comparison, my dear friends. Always remember this. So NMe thrice, okay, will be having the highest tendency to give away electrons, and therefore it is going to be the strongest Lewis base. Alright, so this is, my dear friends, under complex formation reaction, and as I already told you that this is the last chemical property of organometallic compounds, and with this we come to the end of this particular chapter as well. Alright, and the entire sessions I've explained you about. First of all, to start with, what exactly you mean by organometallic compounds. Then we went into its classification. Then we discussed about its 5 methods of preparation, and then the 5 chemical properties. Alright, I have distributed in various parts so that it becomes easier for you to understand. Rather than making this entirely in one single video, it becomes really very difficult. So I've just segregated it. Okay, in the description box you can go through the description also, that in this particular video which particular reactions I am explaining, so you get a better idea. And also I will try to put up the link of the previous videos also, so that it becomes very clear to you. So I hope you have understood this chapter very well. Thank you for being with me. God bless you all.